Not all ionic compounds are soluble in water. And we'll go over a list of solubility rules that dictate whether if an ionic compound will be soluble or insoluble. Where this information becomes important is the precipitation reaction. A precipitate is an insoluble solid that is formed by a reaction in solution. Precipitation reactions occur when pairs of oppositely charged ions attract each other so strongly that they form an insoluble ionic solid. So we as chemists want to predict what ion combinations will form precipitates. Some time ago, many gentlemen chemists performed hundreds of reactions. These gentlemen organized their data and summarized results in a table. And from this table, we get a list of rules governing the solubility of ionic compounds in water. Take a look at Table 4.1 from your textbook. These are solubility guidelines for common ionic compounds in water. This table refers to the many summarized experimental observations regarding solubility of inorganic compounds. Let's define what I mean when I'm describing the term solubility. Solubility is defined as the amount of a substance that can be dissolved in a given quantity of solvent at a given temperature. And typically, we describe solubility in grams of solute in 100 grams of solvent at 25 degrees Celsius. That's going to be the standard for most of these ionic compounds here. And I just want to say that any substance with a solubility of 0.01 moles per liter is considered insoluble. And as I said before, not all ionic compounds are soluble in water. So let's take a look at what we call the solubility rules. So for the most part, any ionic compound that is a nitrate, is soluble in water, like sodium nitrate, lithium nitrate, and aluminum nitrate. These are all water soluble. All acetates will be soluble in water. Some examples are sodium acetate, acetic acid, calcium acetate. These are all water soluble. Now typically, almost all chlorides, bromides, and iodides are soluble in water. Sodium iodide, lithium chloride, calcium bromide are all soluble in water. There are some exceptions though. Ionic compounds that are composed of silver +1, mercury 2, 2+, and lead 2+ paired with the chloride, bromide, or iodide ion are insoluble in water. Some examples of insoluble halides are all the silver halides, including silver 1 chloride, silver 1 bromide, and silver 1 iodide. Other insoluble halides include lead 2 chloride, lead 2 bromide, and lead 2 iodide. These are all insoluble in water. And the last one here is compounds containing the sulfate ion are soluble in water except for when paired with the strontium ion, the barium ion, mercury 2, 2+ ion, and the lead 2+ ion. So if I had sodium sulfate, that is soluble in water. If I have magnesium or calcium sulfate, those are soluble in water. But if I have strontium sulfate, barium sulfate, or mercury 2 sulfate, or lead 2 sulfate, these are insoluble in water. We have several anions that are typically insoluble, except for when paired with some specific cations. The sulfides tend to be insoluble in water. So magnesium sulfide is insoluble in water. Iron sulfide, iron 2 sulfide, is also insoluble in water. But when the sulfide ion is paired with the ammonium ion, the alkali metal cations, the calcium, strontium, and barium ions, these are soluble in water. So some examples of soluble sulfides are ammonium sulfide, calcium sulfide, strontium sulfide, barium sulfide, and sodium sulfide. Carbonates also tend to be insoluble. Remember in lab when you guys performed the separation of a ternary mixture? Recall that one of the components was calcium carbonate, and this was insoluble in water. Some notable exceptions to this rule is that ionic compounds containing the carbonate ion that are paired with the ammonium ion are soluble, and the alkali metal cations paired with the carbonate ion are also soluble. So ammonium carbonate, sodium carbonate, potassium carbonate. We used potassium carbonate in lab when we separated our ternary mixture. These are all soluble in water. Next is the phosphate ion. The phosphate ion tends to be insoluble except when it's paired with the ammonium ion and the alkali metal cations. Okay, so ammonium phosphate, sodium phosphate are both soluble phosphates. And lastly, hydroxides tend to be insoluble. Copper 2 hydroxide or copper 1 hydroxide is insoluble in water. But there are exceptions when the hydroxide ion is paired with the ammonium ion, the alkali metal cations, calcium 2+, strontium 2+, or barium 2+. So ammonium hydroxide is soluble, sodium hydroxide is soluble, potassium hydroxide is soluble, and the calcium hydroxide, strontium hydroxide, and barium hydroxide are also soluble. So in remembering these rules, try to recall the soluble cations and their exceptions, and the insoluble anions and their exceptions. So why did we go through all of those solubility rules? What is the purpose of learning this? Well, as I mentioned before, as chemists, we want to be able to predict the properties of substances in a chemical reaction. Now that we know the solubility rules, we can now predict whether the products of a reaction will form an insoluble product or what we call a precipitate. One of the most common types of precipitation reactions is called a metathesis reaction or an exchange reaction. Sometimes we call this a double displacement reaction. Okay. Not all metathesis reactions are precipitation reactions, but knowing our solubility rules, we can identify if a precipitation reaction occurs. Let's talk about how the metathesis reaction works. The cation of one component switches places with a second cation in a reaction. Look at this generic reaction right here. AX plus BY produces AY plus BX. Notice the only thing that happened is that the A and B switched places. The A was paired with the X and is now paired with the Y. And B was paired with Y and now B is paired with X. Let's now talk about how we can predict the products of a metathesis reaction. First, we must find all of the compounds that dissociate in water and break those into aqueous species into ions. What's going to do is show how these ions actually exist in solution. And if we see anything that is a solid, we leave that as it is because it doesn't dissolve in water. Let's use this example given here when magnesium nitrate and sodium hydroxide react. So our first step is to determine which ions are present and when the reactants dissolve in water, and we write the formulas for the products. For our example, when magnesium nitrate dissolves in water, it breaks apart into one magnesium ion and two nitrate ions in solution. the sodium hydroxide will break down into one sodium ion and one hydroxide ion. So these are our reactants in solution. What happens when these ions come into contact with each other? They could either stay as ions or they could combine together to form a precipitate. The solubility rules will help us determine what's going to happen in a particular reaction. In this case, sodium and magnesium don't combine because they're both cations. The magnesium ion will come together with the two hydroxide ions to form magnesium hydroxide precipitate. Will the sodium and the nitrate ion come together to form a precipitate? They will not, because our solubility rules tell us that all nitrates are soluble. So our products of this reaction are magnesium hydroxide and aqueous sodium nitrate. Now we can put together the products and the reactants. Magnesium nitrate reacts with sodium hydroxide to form magnesium hydroxide precipitate and sodium nitrate. Now this reaction is not balanced. We need to balance the reaction. So if we put a 2 in front of the sodium hydroxide and a 2 in front of the sodium nitrate, that balances our equation. There are a few ways to write metathesis reactions. First is what we've been writing all along. This is what we call the molecular equation, right? Reactants on the right, the products on the left, without indicating the ionic nature of the compounds, only giving the overall reaction with states of matter. We'll have other ways of expressing metathesis reactions, and that's the complete ionic, which we'll talk about in the next slide. So for example, here we have our lead nitrate that's aqueous plus 2 potassium chloride that's aqueous produces lead 2 chloride that's a solid plus 2 potassium nitrates that's aqueous. So this is what we call a molecular equation. There is an alternative way to write metathesis reactions, and this is to write what we call the complete ionic equations. And to write a complete ionic equation, you write all strong electrolytes dissociated into their ions. Now, in the beginning of this lecture, we described what a strong electrolyte is, and that is a strong acid, strong base, and all of the soluble ionic salts. Why would we want to do this? Well, writing an equation more accurately reflects the species that are found in the reaction mixture. So lead nitrate is soluble, so that dissolves or dissociates into lead 2+ and 2 nitrate ions. Okay, and potassium chloride dissolves into 2 potassium ions and 2 iodide ions. Now, lead iodide is insoluble, so we don't separate this one because it's insoluble. And lastly, we have 2 potassium ions and 2 nitrate ions. So we write our complete ionic equation as aqueous lead 2+ plus 2 nitrate ions that are aqueous plus 2 potassium plus 1 that's aqueous plus 2 iodide ions that's aqueous produces lead 2 iodide plus 2 potassium ions that's aqueous plus 2 nitrate ions that's aqueous. So this is our complete ionic equation. And in the next slide, we'll write the net ionic equation. And the last way we have to write metathesis reactions is the net ionic equation. In the net ionic equation, we don't write all of the ions that are found on both sides of the reaction arrow. These ions that are found on both sides of the reaction arrow are called spectator ions. So for example here, the potassium and nitrate ions are spectator ions. And we see these ions in both the reactant side and the product side. So we don't write in the nitrate ion or potassium ions on either side of the reaction. We just write lead 2 plus aqueous plus 2 I minus aqueous produces lead 2 iodide solid. And that's how you write net ionic equations. Remember that in the net ionic equation, we only write the ions and molecules that participate in the reaction. We use these net ionic equations for a few things. And the net ionic equation generalizes our reaction. In general, for any reaction that has lead 2 plus ions and iodide ions forms lead 2 iodide. It also focuses the attention on the change that is occurring in the reaction. Being able to write molecular, complete ionic, and net ionic equations is going to be something they return to often. So it's important to understand the concept and to really know your solubility rules. So here we can summarize how to write net ionic equations. First, write a balanced molecular equation for the reaction. Rewrite the equation to show the ions that form in solution when each soluble strong electrolyte dissociates into ions. Only strong electrolytes dissolved in aqueous solutions are written ionic form. Identify and cancel any spectator ions.